Welcome back after the break. So, we do have this slide which is, as I said, a very busy slide. So, what we have seen is that by considering the base loop, we can find the base current, and then we can proceed for finding the collector current, and then we consider the collector loop. So, this is the base loop, and then we do have the collector loop. So, this loop it is getting completed by whatever the DC voltage we are connecting here with respect to ground. So, now let us see, instead of giving the voltage here by this means, let us see what are the different ways the signal can be given to the base of the transistor, and let us see what is its different implication for different cases of applying the the voltage at the base. So, here we are throwing this new words called common emitter circuit configuration. So, let us see what it is. So far we are discussing about this transistor. It is at the base we are connecting something, and then at the collector we are observing its corresponding effect, while keeping voltage at this node some DC voltage with respect to ground. Now, here if I give a voltage directly at the base, and let you call that we are applying a voltage here, and let you call this is input voltage, and if we vary this voltage, the corresponding effect we like to observe at the collector. So, we may say that okay, we are observing the effect at the collector, and hence let you call this is the output port, and and then this is input port. So, the voltage you are applying here, we are calling it is V in, and the corresponding effect we will be observing at the collector with respect to emitter, let you call this is V out. Now, we have discussed that what are the things it will happen for a given voltage at the base. So, in case if the voltage it is directly coming to the base, we have said that at the base side we do have IV characteristic. So, that gives us basically the base current. So, if I say that this is the V in, which is incidentally same as VBE of the transistor, and we know that this is having either you may say exponential in nature, or we may say that we can approximate by linear line or whatever it is. So, then from that we multiply with beta f to get the corresponding collector current. So, what we are getting here directly, if I write that this is the IC versus the same V in. So, we are getting the IC versus V in like this. So, based on this scaling factor, the corresponding scale here it will be different, but the nature here and this one it will be essentially same. So, we may say that based on this condition we are getting the corresponding collector current. Now, if you see the output port which is having the equivalent circuit like this, if I ignore the early voltage effect, so we do have RC, and then we do have the VCC, and then we are observing the corresponding output voltage here. So, you may call this is V out, that is what we are calling, and incidentally that is same as VCE. So, if we draw the IV characteristic of the output port on the other hand, namely the IC versus VCE characteristic. So, which means that for a given value of current, say or let me start from here. For a given value of V in, say at this point, we multiply with beta f, then we are getting the corresponding collector current, and this collector current is giving us at the output terminal, and that current is flowing through this RC. So, if I ignored, as I said, if I ignored the early voltage, then we may say that the collector current, it is almost independent of this VCE, and so the you may say that pull down element characteristic, it is you can say it is horizontal. On the other hand, the load line, namely the characteristic of the RC, it is giving us the corresponding load line. Okay. So, now this is what earlier also we have discussed. Now, see what are the things it will happen in case if we are changing this voltage. So, so far for a given value of V in, we are getting the corresponding solution here, namely the same collector current is coming here, and then we are finding the solution here, which is VCE, incidentally that is equal to V out. Now, if I increase this say input voltage by some amount, which means that VBE of the device, it is getting changed to some other value. So, from this point we are moving to this point. So, likewise the corresponding collector current is also changing up, which means that its corresponding characteristic, or what we say that pull down element characteristic got shifted up, okay, assuming that the device it is still in active region, particularly while it is crossing this load line. And while we are increasing the input voltage, the characteristic of this RC did not change, only pull down element characteristic it got changed from the violet color to the blue color. So, due to this change of the V in, what you can say that this intersection point got changed to this point. In other words, the corresponding output voltage now it got changed to this point. So, let me put a number here. So, let me call this is the first case. For first case we do have this current. So, let me write this characteristic is for the first case, and the corresponding V out here it is, we call it is V out 1. So, this is also first case. Now, the second one, let me use a different color here. So, now we are at this point. So, that means at the input we are applying V in 2, earlier it was V in 1. So, now we are at this point, and then the corresponding characteristic also got shifted up, and the intersection point going from this point to this point. So, we call this corresponding output, it is say V out 2. So, likewise, if on the other hand, if we decrease the input voltage to a lower value, say here, let me call this is V in 3. So, that gives us say collector current somewhere here, and that gives us the pull down characteristic here. So, now the intersection point it got shifted here. So, initially it was here, it got shifted to this point, now it got shifted down on the other direction to this point. So, the corresponding voltage here will be calling say Vout 3. So, if I vary this voltage and if we monitor or if you observe this voltage, we can see that this variation it is creating an effect here, and this effect if you see here incidentally while we are increasing this voltage, the voltage here it is decreasing and vice versa. But most important thing is that if we change a small amount here, the corresponding variation here it is more. In fact, it is related to the slope of this line or slope of this line and slope of say the load line. In other words, if I vary this V in and if I create the corresponding change in I c. So, if I vary this V in like this, the corresponding effect here it is in the current also it is coming here, and that makes this characteristic is also going up and down and making this voltage it is remaining on this load line. However, it is going from this point to this point. As a result, the corresponding output, corresponding effect it is coming like to the output in the amplified form. So, if I say that this is the cause, if I say this is the cause or input, maybe signal input called say small v in, and the corresponding variation here whatever we are getting here it is the V out. So, based on as I said that based on this slope and based on this slope we can say that signal it is getting amplified. So, you may say that it looks like there are two mirrors, say this mirror, okay. It takes this signal, converts the voltage signal in the form of current. So, depending on the slope of this line, you can see that for a given variation here it is having good amplification, and then this variation it is coming to this y axis, and then load line it is working as another mirror working in opposite direction, namely converting current into voltage. So, if the slope of this mirror it is very stiff compared to this mirror, then we will be getting the amplification. So, intuitively you can see that this I V characteristic, which is of course, it is exponential, which is having very sharp slope, and on the other hand this line slope of course, it is decided by 1 by R c. So, relative slope of these two so called mirrors, they are providing a gain. So, if I say that slope of this line it is G m called transconductance of the circuit. Why is it called transconductance? Of course, it is current to voltage to current relationship. So, that is why it is conductance, and also it is relating input voltage to output current or collector terminal current, that is why it is called transconductance. And then if I consider the slope here, it is 1 by R c. So, if I combine this slope here 1 by R c and this G m together, and of course, it is bringing back this the current to voltage. So, in fact, if I take reciprocal of this one, that gives us the overall gain, namely this divided by V in. So, V out by V in is this G m divided by slope of that line 1 by R c, or this R c it is directly coming here, So, you can say that this is Gm into Rc. So, instead of writing like this, we can directly write Gm into Rc. So, that gives you some idea that how this circuit can be utilized as an amplifier. So, we are getting a notion of amplifier. So, instead of changing this voltage slowly, if we vary rapidly, probably we can find nice amplification. So, let us see. Yeah. So, we do have the same circuit here. So, instead of giving the DC signal, we may call this as V in, and whatever the things we are observing here, we call it as V out. And as we have discussed in the previous slide, so if I vary this input over a wide range, so if I vary this input over a wide range, what we have seen is that I see it is changing with respect to V in, and this change it is coming to the output port. So, I c versus V c e, which is of course incidentally that is V out. So, this characteristic curve, it is after multiplying with beta, it is getting as output characteristic like this. And so, for different input, if I consider the corresponding output, of course, let me draw the load line. So, this load line, of course, this is slope, it is 1 by R c with a minus sign. This point is V c c, and what we said is so far we are talking about input. If we change over a small range, then we have said that the corresponding the pull down characteristic also getting shifted up or maybe shifted down, and so and so. But then if I vary it, if I vary this input over a wider range, say for example, if I take this variation even a smaller value, so the corresponding output characteristic it will be like this. So, the corresponding voltage here, output voltage may get stuck at VCC, particularly if the V in is less than this point, you may call this is whatever cut in voltage or VBE on. Okay. And if the input voltage is less than that, of course, the output is remaining there. On the other hand, if the output is going beyond certain level, so it may be going very high here, and the corresponding pull up characteristic it may be like this, corresponding to say this point, and that may be making the transistor entering into the saturation region, and the corresponding output it will be almost remaining close to 0. So, if I vary this input over a wider range, and then if I observe the corresponding output here, so this is corresponding to the middle one, this is corresponding to this point, and this is corresponding to say this point, and so and so. Then whatever the behavior we observe, namely, let me use this space, V in to V out characteristic, that we get something like this. So, till V in is VB on, the corresponding output it is stuck at VCC, and then it goes down fairly in linear way, or rather whatever the characteristic we do have here. And then again once the device it is entering into the saturation region, output remain close to ground like this. So, this point is corresponding to this point. On the other hand, once you exceed say beyond some point here, we are going to this point. So, you may say that in the middle range the behavior, input to output transfer characteristic behavior, it is quote and unquote linear. On the other hand, if you are going here, due to this part the input to output transfer characteristic it is getting saturated. On the other hand, due to the other side, due to this part is getting saturated. So, this nonlinear behavior it is coming from the trans characteristic nonlinear part, and this nonlinear part it is coming due to the output port characteristic. And on the other hand, in the middle we are getting fairly good linear part. So, whenever we are considering say this circuit as an amplifier, what we like to do here it is we like to keep the device in this middle portion, preferably with respect to a middle point here, and then input will be varying with respect to that, and we should rather avoid this part and this part where the signal it is getting clipped. There may be different application, specific application where we may push this device into this two nonlinear part, but unless otherwise it is stated, for analog circuit we prefer to keep the circuit here. And how do you do that? We make sure that V in it is beyond V B, and also the VCE it is such that the device it is not entering into the saturation region. You may be you may recall that one important thing is that in this portion the device the device is entering into a region where the input to output transfer characteristic it is getting saturated. So, in other words you may say that if I want to use this circuit as an amplifier, its corresponding output is getting saturated. That is why this portion if the VC is less than some value called VCE set, if it is less than that we call it is the device it is in saturation region. So, now at least we are moving to a direction that we will be keeping the device at some stable point called Q point or operating point. In other words, we like to keep the device somewhere here called whatever it is Q point. So, you may say that the corresponding pull down characteristic it is basically this one, and then with respect to that we like to vary the input plus or minus with respect to the Q point, and as a result we will be seeing the corresponding intersection point of the pull down characteristic and the load line it is going up and down, which is making the corresponding output here. So, in other words you may say that instead of considering this signal as DC, we may say that it is having some sinusoidal part and then also it is having a DC part. And this V in we may say that small signal part or the signal part we denote by small V in, and on the other hand the large signal part or the DC part which is defining the operating point by say capital V B E or whatever capital V in. Let me write here capital V I N. So, you may say that this capital V small in it consists of this part small signal part as well as the DC part, and the DC part should be such that this operating point should be in the middle, preferably in the middle of the suitable range of the input to output transfer characteristic, and then we apply the signal with respect to that. And likewise, at the output, whatever the voltage you will be observing, corresponding to this DC, it may be having a DC part called capital V small out, and then it is also having influence of the small signal, and the corresponding influence or effect we call small V out. So, we will say that this is the small signal part. So, this input to this output, of course, we are expecting a gain, and again what did we say, that the slope of this mirror or this trans characteristic to the load line slope, or whatever we say, this mirror, they are defining the gain of this V into V out. So, end of it, what we are getting is, so we are having, this is V out, small V out, and this part it is small V in, and V out divided by V in is essentially slope of this line, which is G m, divided by slope of this line, which is 1 by R. So, it is coming R C. Of course, it is having a minus sign. So, that makes a minus sign here. So, you may say that the circuit gain, it is minus G m into R C. And as I said, that we do have a notion something called amplification. So, this circuit, it is providing a good gain, and we call this circuit, it is common emitter. That is because the signal we are applying here at the base, and we are observing the output at the collector, and the emitter, it is connected to either DC voltage, or in this case it is ground. So, we may say that for the signal emitter, it is also working as a reference terminal, and that is why you call it is common emitter amplifier. Note that emitter need not be connected to ground, as long as this emitter it is connected to a constant DC voltage, then also we call it is common emitter amplifier. Yeah. So, there will be different other configurations, but before we go into that, let me summarize whatever we have discussed here. So, let me rather use different slide here. So, at the input, as I said that we do have a DC part, and then we do have a small signal part together, and it is creating an effect here, which is having a again the corresponding DC part, and then it is having a small signal part. And from the input to output transfer characteristic, what we said is so this is capital V small out, and x axis is capital V small in, and as I say that it is having fairly non-linear part initially, and then it is having a linear part, and then it is getting saturated like this. And at the input whatever we are saying that V capital in is basically capital V capital in, that gives us capital V capital out, and with respect to that we do have if we apply some input, so with respect to that we are applying input here. So, that is small v small in, and the corresponding effect we are getting here it is variation of the V out, and we call this is small v out. Now, so we may say that for every time this is our reference point. So, if I change this V in over this range and to find the corresponding solution, either we can use this nonlinear characteristic curve every time, or the better option is that since we are interested of the small signal to this small signal output, probably it is better to consider only this segment of the characteristic curve, and we can confine our discussion with respect to that. Namely, let you consider now this is small v in to small v out, and this whole characteristic now it is getting shifted to the origin. So, you may say that the characteristic it is only this part. So, this point it is coinciding with this origin, and this segment of the transfer characteristic curve it is here. So, every time if we ensure that this operating point is not changing, that means this point is not changing, and then if you have any signal here ensuring that this q point is not changing, then this characteristic curve it is sufficient. And slope, of course, slope of this characteristic curve, as we said that this will be g m into r c with of course a minus sign. So, that is the slope of this characteristic curve, and so from that we can find what will be the input to output relationship. Of course, if you go beyond this one, then there will be nonlinear part which we are not interested in. Since we are suppose if we ensure this q point always align with this this origin of this small v into small v out transfer characteristic, then we may say that the analysis of the circuit it will be much simpler, which means that if we draw the corresponding equivalent circuit, so instead of if you see the device large signal wise, we do have this model of the BJT. So, this is the base terminal, and then this is the emitter terminal, and this is the collector terminal. So, this circuit, of course, we do have RC connected there, and this model it may be simplified or linearized. So, when you may recall that this consists of one on resistance, and then the cut in voltage, in this case we call this is VB on, and this is base to emitter resistance called R pi. So, whenever we are shifting this q point to this origin, equivalently saying that we are dropping the DC part, that means we are making this is ground, this is also ground, and we are also probably will be getting this also ground, and not only this external DC voltage need to be dropped, but whatever the internal DC voltage is existing within the model itself, that also need to be dropped. So, the whole circuit now it becomes simpler, like we do have R pi here. So, this part it is getting dropped, and then here we do have I may say this is remaining current control current source. So, here now it is only the signal part we will consider. So, we use small I c, which is beta times I b, where I b it is the small signal current flowing here. So, then of course, we do have the R c connected here, but then R c it is connected to DC voltage, which is AC ground. Emitter node anyway it is connected to ground, and at the input the signal, whatever the signal we are applying here, that is the input signal, and the DC part it is getting dropped out. So, we may call this is the V in, and the corresponding voltage we will be getting here, it is called the small signal V out. So, instead of using this model, now we are going to use this model. So, similar to diode, here also we do have a notion called small signal equivalent circuit, which is also giving small signal model of the whole circuit. And once we translate this into small signal equivalent circuit, as I said that we are simplifying the circuit not only by just dropping the DC part, but also making all of the DC component internal to the device are also getting removed. And most important thing is that since this characteristic curve it is going through the origin, that means input to output relationship it is linear, and hence superposition theorem can also be deployed once we consider this this simplification. Only thing is that we have to ensure that this Q point is not getting shifted. So, along with the signal amplification, we are also getting a notion something called small signal equivalent circuit. So, this is referred as small signal equivalent circuit. Okay. So, we will be later on we will be frequently using this model. Only thing is that you need to be of course, we have to consider this model to get the value of the DC current and to get this GM. Of course, this GM it is a strong function of the DC collector current. So, we will be discussing that later, but just to highlight that in our later examples those are the things will be discussed more. Now, probably we can try out one numerical solution, numerical examples. So, suppose we do have a circuit like this. Let you consider this is 10 volt, and let you consider VBE on equals to 0.6 volt, and at this point we are connecting a DC source through RB, and let you say this is 5 volt, and let us say that this RB equals to maybe 40 okay 440 kilo ohms, and beta is equal to say 100. Then and also RC equals to say 2 kilo ohm. Then can you find V out? So, how do you proceed? First thing is that we need to find IB by considering this RB and BB on and then 5 volt. So, you may say that IB solution wise. So, IB equals to 5 volt minus 0.6 volt divided by 440 K. So, that gives us 10 microampere, and then I c equals to beta times I b. So, that gives us 1 milliampere, and then drop across R c equals to I c into 2 kilo ohm. So, that gives us 2 volt. So, the V out, which is 10 volt VCC minus 2 volt, that is 8 volt. Now, here of course, here we have assumed the device it is in active region, and since this is 8 volt and the voltage coming here it is close to 0.6. So, definitely base to collector junction it is reverse bias, and hence the device it is in active region, and hence everything is consistent. But of course, if I increase this R c, then and if this drop it is approaching towards 10 volt, the device it may be entering into the saturation region. Now, on top of this one, if I say that if I feed a signal here at the base, then what it may happen. So, probably today we are running short of time. So, let me consider that example maybe next day. So, what we have covered so far, we have analyzed nonlinear circuit containing BJT, and we started with 2 examples where we have applied voltage at the base, and then we have observed the corresponding current at the collector, and then the corresponding output voltage. Then we have entered into some circuit called amplifier, where we see that the circuit is having a specific name called common emitter configuration. We also have observed that input to output large signal characteristic of the common emitter amplifier, and then portion of the large signal characteristic can be considered as small signal input to output transfer characteristic, and slope of the transfer characteristic which is we have seen that it comes from the GM and the load R c together to define the slope of that, and that is making if it is higher than 1, that is making the circuit as an amplifier. So, we have seen that notion of signal amplification by this common emitter amplifier, and we have given a slight hint of moving to small signal equivalent circuit and small signal model of the BJT. So, later on we will be discussing that part further detail. We just gave a small example, numerical example. We will be having more examples later on. I think that is all I do have today. Thank you for listening.